This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is reactive impedance. Our objective is to quickly discuss why reactive elements like capacitors and inductors present impedance to AC sources. We'll discuss why current leads or lags voltage for reactive elements and how frequency and component value influence current magnitude. This lecture operates under the presumption that viewers watch the capacitive complex impedance, the inductive complex impedance, and AC Ohm's Law lectures, all available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. If you're adept in the skills as presented in the aforementioned lectures, you can no doubt easily numerically calculate the complex impedance of a capacitor or an inductor with a given component level value and an excitation frequency. Additionally, you are undoubtedly capable of using AC Ohm's Law to calculate current given voltage and impedance values, or vice versa. The intention of this lecture is to step away from the numbers for a bit and simply consider why reactive elements like capacitors and inductors behave the way they do in AC systems. Sit back, relax, and enjoy the tour. Let's take a look at capacitors first. Recall from our discussions about time-variant DC responsive capacitors that initially uncharged capacitors experience a surge of incoming current, followed by rising voltage. Similarly, a discharging capacitor experiences an initial surge of outgoing current, followed by falling voltage. This behavior can be summarized as current leading voltage for capacitive elements, and that the current spikes occur before a change in voltage. This is essentially the same reason capacitors exhibit a phase shift between voltage and current in AC systems. During the charge phase, current rushes into the capacitor and capacitor voltage rises. During a subsequent discharge phase, current rushes out of the capacitor and capacitor voltage drops. The problem in identifying the present state of a capacitor in AC systems is that the polarity in AC systems cyclically oscillates at a frequency too fast to allow a technician to change the leads of a voltmeter or ammeter to adequately reflect the actual state and polarity of the capacitor. Consider a capacitor in an AC system with an ammeter and voltmeter in the following locations. The ammeter is oriented in to out, left to right, and the voltmeter is oriented positive to negative, top to bottom. Because we can easily lose ourselves in semantics, just think of voltage in terms of absolute magnitude, i.e. forget the sign. If voltage absolute magnitude is increasing, the capacitor is charging. If voltage absolute magnitude is decreasing, the capacitor is discharging. Let's take a look at a full cycle of an AC waveform in quarter cycle increments. The first quarter cycle is characterized by rising voltage. This capacitor is charging. The next quarter cycle is characterized by falling voltage. This capacitor is discharging. The next quarter cycle is characterized by increasing voltage magnitude. This capacitor is again charging. Finally, the last quarter cycle is characterized by decreasing voltage magnitude. This capacitor is discharging. The first half of the cycle is easy to explain. The initially uncharged capacitor at first experiences a large surge of positive or incoming current. As capacitor voltage rises, current decreases in magnitude and then stops altogether when the capacitor reaches full charge. The fully charged capacitor then starts to discharge. As capacitor voltage drops, the capacitor experiences negative or outgoing current. Here's an important switchover. Once a capacitor fully discharges in one direction, it seamlessly transitions to another charge cycle, only this time in the opposite direction. Pay attention to the orientation of the ammeter in to out, left to right, and the voltmeter positive to negative, up to down. The uncharged capacitor experiences a large surge of incoming counterclockwise current. Given the orientation of this ammeter, this will be considered negative current. Capacitor voltage rises, and given the orientation of the voltmeter, this will be considered negative voltage. The fully charged capacitor then starts to discharge. As capacitor voltage drops, the capacitor experiences outgoing current. Given the orientation of the ammeter, this will be considered positive current. Capacitor voltage drops and the cycle begins anew. Before we move on, allow me to briefly discuss the concept of power. I know we haven't explored AC power yet in its full complexity. However, consider this very basic understanding that quite like DC power, that instantaneous power is a product of instantaneous voltage and instantaneous current. The first quarter cycle is characterized by a period of positive voltage and positive current. Positive times positive is positive, meaning the first charge phase is an expenditure of positive power. This means the supply is delivering power to the capacitor, and the capacitor is storing this accumulation of energy in an electrostatic field. The second quarter cycle is characterized by a period of positive voltage and negative current. Positive times negative is negative, meaning the discharge is an expenditure of negative power. What is negative power? If positive power is defined as the source delivering power to the capacitor, one might define negative power as the capacitor returning that accumulation of stored energy back to the source. In a perfectly efficient system, all energy stored in the previous charge phase would be returned to the source during the subsequent discharge. In the real world, however, we might expect there to be losses in the system. However, for today's purposes, let's consider this a mathematically perfect entity, unbound by the constraints of reality. The charge process was a period of positive power and energy storage. The subsequent discharge was a period of negative power and energy return. There is an equal and opposite exchange, and in the end, no real work was done. However, current did flow from the source to the load and back again. This type of positive and negative exchange of power is called a reactive interchange, something we'll explore at length in later lectures. The second half of the cycle is a repeat of the first half, only in the opposite direction. The next quarter cycle is characterized by a period of negative voltage and negative current. Negative times negative is positive, meaning this charge is an expenditure of positive power. Supply is again delivering power to the capacitor for 1/4 of a cycle, and the capacitor is storing this accumulation of energy in an electrostatic field. Finally, the last quarter cycle is characterized by a period of negative voltage and positive current. Negative times positive is negative, meaning the second discharge is again an expenditure of negative power. As previously, negative power means the capacitor returns the previously stored energy to the source. A single cycle of sinusoidal AC therefore consists of 2 complete charge and discharge cycles, 2 bursts of positive power, and 2 equal and opposite returns of negative power. Long story short, current leads voltage for capacitive elements because a change in current must precede a change in voltage as the capacitor stores and releases energy in its associated electrostatic field. I say again, current leads voltage for capacitive elements. This is why a purely capacitive element always experiences a current waveform 90 degrees in advance of the voltage waveform when calculated using phasor equivalence. For example, given a 15 microfarad capacitor at an excitation frequency of 60 Hz, this capacitor presents a complex impedance of roughly 176.8 ohms at an angle of negative 90 degrees. Let's say this capacitor is known to experience a voltage differential of 50 volts at an angle of negative 15 degrees. I am absolutely confident that any manipulation of Ohm's law will demonstrate current will lead voltage by a relative 90 degrees. Current should therefore have a phase shift of 90 minus 15 degrees or positive 75 degrees. An application of AC Ohm's law, solving for current, where current is voltage over impedance, demonstrates we should anticipate this capacitor will draw roughly 282.7 milliamperes at an angle of positive 75 degrees, consistent with our expectations. One can use this fact as a means of checking your work. If you get a phase shift between voltage and current of anything other than 90 degrees, it means you are doing it wrong and you need to revisit your work. Now that we've got a general understanding why current and voltage are out of phase with one another for capacitive elements, let's discuss how capacitive component magnitude and frequency influence impedance and thus current. Your base understanding of Ohm's law demonstrates that given constant voltage, low impedance elements will draw large amounts of current, whereas high impedance elements will draw small amounts of current. This should be well within your capacity to understand on a very instinctive level. You'll additionally recall that the magnitude of capacitive complex impedance is 1 over 2 pi times the frequency times the capacitance value. You'll note frequency and capacitance are in the denominator of the complex impedance formula. The influence of these two properties can be most efficiently illustrated using a graph of capacitive complex impedance as a function of frequency. Given constant capacitance, small frequencies result in large capacitive impedance magnitude. Conversely, given constant capacitance, large frequencies result in small capacitive impedance magnitude. Frequency is the rate of polarity oscillation. Lower frequencies correspond to slowly changing waveforms, where 0 Hz, or no change, represents DC. Capacitors at low frequencies present large impedance. Think about it. What's the steady state impedance level of a capacitor in a DC system? After the transient charge phase ends, a capacitor essentially appears like an open circuit or an infinite impedance. After a capacitor is fully charged or fully discharged, current flow ceases. The complete halt of current flow perfectly defines a high impedance element. This makes sense. Above DC or 0 Hz, slowly oscillating waveforms present slowly changing voltage. As a result, the charge or discharge process doesn't have an incentive for a massive exchange of current, i.e. current is low at low frequencies, synonymous with a high impedance element. This lack of incentive to charge or discharge results in sluggish, low magnitude exchanges of current. Conversely, at high frequencies, quickly oscillating waveforms present rapidly changing voltage. As a result, the capacitor has a high incentive to rapidly charge or discharge, resulting in massive exchanges of current, i.e. current is high at high frequencies, synonymous with a low impedance element. If you think about it, capacitors in high-frequency systems are always in the early stages of a charge or a discharge, synonymous with a high burst of current. Now that we've got an understanding of how frequency affects impedance, let's discuss how capacitance component magnitude influences impedance. Capacitance is in the denominator of the capacitive complex impedance formula. Given constant frequency, high capacitive elements present low impedance, whereas low capacitive elements present high impedance. This is a reflection of capacitor construction. Large capacitors are physically larger and have a lot of room for charge. As such, they draw a large amount of current. This is synonymous with a low impedance element. Conversely, smaller capacitors are physically smaller and don't have a lot of room for charge. As a result, they draw less current, synonymous with high impedance elements. All right, that about wraps it up for capacitors. We learned why current leads voltage or capacitive elements and how frequency capacitance influence impedance. Let's do the same thing for inductors. It's really more of the same, except we're dealing with magnetic fields instead of electrostatic fields, lagging current instead of leading current, and impedance magnitude that increases as a function of frequency and component value instead of decreases. If you want to think about it this way, inductors are the opposite of capacitors and vice versa.